So the UNIO solver lives pretty much entirely in Rusty trait selection source solve and Rusty middle solve. Wait, I have to move that one out of the way. Yeah, Rusty middle trait solve. This contains all the data structures and the implementation of the cache, and pretty much everything else is in Rusty trait selection. So there's only, well, there are two ways to enter the solver. For coherence, only one is relevant. There's evaluate root goal. And then there's select a new trait solver. But as we don't use selection during coherence, that one is only necessary for code when resolving instances and for coercions. So the only relevant entry point is, where is it? Here it is. Is evaluate root goal on the inference context. And that so everything, everything inside of the solver is happening inside of the eval context, which is just the God object, which contains all the relevant information necessary for the canonical queries. And also when we evaluate a nested goal, that also always uses the eval context, which means that when we compute a root goal, we have some dummy context, which is, its fields are a bit weird in parts because it's really just a skeleton so that we can call evaluate goal. And that's what we do whenever there's any nested goal, or the goal is an obligation without a cause. So an obligation, but no diagnosis information because it's relevant. We can recompute it anyways later. So we call evaluate goal. That one takes a goal and some stuff which you don't have to care about, and then calls evaluate canonical goal, which canonicalizes and then does a lot of magic, which is completely irrelevant for most of what we're doing, and then calls compute goal. Compute goal for each goal kind calls a nested function which handles that goal kind, where most of them are quite straightforward and also match the old solver. For example, looking at trait goals, they have two steps. We assemble candidates, then we merge the candidates, and assembling candidates is one big function with a few interesting design constraints. So the first one is if you have any trait goal and the self type is ambiguous, we always fail with ambiguity. So what this force ambiguity function does, it creates a single candidate which is ambiguous. And when we then merge that candidate, we just have ambiguity as the final result. I guess for that to make sense, what does the trait solver return? The trait solver returns a query result. A query result is either no solution, if the goal definitely, in coherence it's definitely, but outside of coherence we can sometimes return no solution even though there would be one, which is great. But there's no solution in case a trait bound is not implemented, or we cannot normalize, or something's not performed. And then if it might be well formed, we return a canonical response, where a response is our certainty, which is either yes, in which case the goal definitely holds, and we don't have to try again at any point because it's now done, or it's ambiguous, or maybe, which is either the case because of overflow, or because we are like at some point we're stuck. Like there are multiple candidates which could hold, or we have to prove some goal on an inference variable. In these cases, we return ambiguity. And finally, some external constraints, which are like region constraints and some opaque type stuff, which we should probably also talk about at a different time. So yes, we either return yes or maybe, like yes or ambiguity. And we also return the inference constraints. So if a goal would constrain some inference variable to U32, that would be part of the canonical response using the var values, which is like canonicalization, where there should be a chapter for that in the dev guide, hopefully. Yeah, sure.
So in contrast to the old solver, instead of just constraining the inference variables in the inference context and then in the end kind of figuring out that information and passing it out of the query, we always figure out when we are binding an inference variable to a concrete type and store that information.
So yeah, in the old solver it kind of happens implicitly, where because the auto-rate solver is like it computes the goal in the same inference context. It just constrains inference variables, and then that gets propagated out. But because we always canonicalize, that's explained in more detail in the dev guide, but pretty much for each inference variable in the input, we have we put all of those in an array while canonicalizing the goal. And inside the query, we also have that array, like the var values array. So, and these start out as all the inference variables from the input. And then during the canonical query, like some of these inference variables get constrained. And we then at the end take that array and canonicalize it again as part of the response. So if an inference variable gets constrained inside of the query, now this var value array contains like U32 instead of the inference variable. And then when we instantiate the canonical response, we equate that U32 from the response with the inference variable like from the caller, and that way we propagate the inference constraints outwards. Which is like a lot of information at once, but does it kind of make sense?
To me, it does. I mean, that's how canonicalization worked even before the new solver, but we were really rarely using it.
Yeah. So that's the basic idea, and it has one very significant advantage, where in the old solver, so in the old solver, what we do is we assemble all possible candidates, but because we don't canonicalize, we either immediately apply the constraints in the context of the caller, or we have to discard them. We can't stash them for later. So assembly, use a candidate, checks some impl, tries to use an impl, proves its nested goals, its nested whereabouts, and then once it figures out whether it might hold or whether it would definitely error or whether it's ambiguous, it discards all of the inference constraints and only remembers whether it definitely holds or whether it's ambiguous. And then after doing that for all of the possible candidates, we check whether we can filter it down to a single one. And if we do, then we recompute everything again to actually apply the inference constraint this time. But in the new solver, because of canonicalization, we can just assemble our candidates, recursively prove them, get all of their constraints as part of their canonical response. And then once we like merge those or get down to a single canonical response, we can then just instantiate it and don't have to recompute anymore. So that's one of the biggest advantages of canonicalization, that we don't have to need this like separate assembly and confirm step, which we have in the out solver, but during assembly we can already confirm. So it saves us some work and also makes the code a lot nicer. And yes, so that's what we do. Okay, so continuing with trade goals, because like these are probably by far, well, normalization is the most involved thing, but trade goals are the most useful thing to know. So we start by evaluating candidates and figuring out for each candidate what are the inference constraints, and does the candidate definitely hold, is it ambiguous, or if it like results in an error, we just throw it away. So we do that by trying to completely normalize the self-type, so structurally normalized tie. As long as the self-type is an associated type, we normalize it until it's either rigid, so we definitely know that it can't be normalized anymore, or until it's an inference variable and we pretty much have ambiguity here. So yeah, if the self-type is not some known type constructor, so either an inference variable or an associated type which normalizes, which may normalize and we don't know yet, so it also results in an inference variable, we just fail with ambiguity. And if not, we assemble a bunch of candidates. So let's look at assemble non-blanket impl candidates, which is responsible for all the trait impulse which are not for some generic parameter t or for a projection, which allows lookup to be far more performant. So what we do is we look at the self-type, which we now know to be rigid, because if it's not rigid, we fail it with ambiguity up here. And using that self-type, we look up the simplified type. And for integer inference variables, we look up the simplified types for all existing integers, which is a bit more involved. Oh well, it's a bit more code. It's not really a lot more involved. So what we then do is we look at all of the impulse for the given self-type. For each impl, we use consider impl candidate, which for trait goals does some performance optimization, checks the impl polarity, which doesn't matter, and then enters a probe, which means that any inference constraints from inside of this don't propagate outwards, which is all right because in this last line, we canonicalize using all these inference constraints, so we don't need them after that anymore. And we don't want like this candidate to infect other candidates, so each candidate is evaluated in its own probe. Where a probe is just the same as inference context probe. Once we leave it, all of the inference constraints get discarded. So for impulse, we take the impl header, replace all generic parameters with inference variables, and then equate the trait ref of the goal with the impl header, prove all nested where clauses, and we don't eagerly prove where, like if you have a nested goal and then you solve it, we don't eagerly prove it. We instead always use add goals. And what that does is it puts all the goals in an internal storage in the evaluation context. And then only in evaluate added goals, or which is like the select all or arrow pretty much, or well, it's select all or return ambiguity. So yeah, we only evaluate goals when having these explicit calls, and these, like that one, let's try evaluate goals. This one evaluates everything in a loop. So it's very similar to the way the current fulfillment context works, where we loop over all goals, and if as long as there's any goal which like applied inference constraints, we like do one more round until we hopefully reach a fixed point. Or if we hit the overflow limit, we fail with ambiguity, fail with overflow, which is, well, ambiguity. So yes, where track goes, equate, add nested goals, and then evaluate all the goals using pretty much using fulfillment, or yeah, using a fixed point. And then we canonicalize and we're done. And that's the same thing we also do for wherebounds. So for track goals, wait, where's assembly? There is assembly. Yeah. So we look up all the impulse. We look up all the built-in impulse, which, if you look at it, it's just a very long else-if chain on all the built-in traits. And then for each built-in trait, we manually generate the impulse on demand. Yeah. I guess what's a good example impulse built-in copy clone. So copy clone impulse only exists for tuples, closures, coroutines, apparently. So for we only have built-in impulse if we're not able to write one by hand in standard library. So for tuples, what we do is this function collects all of the types which would have also implement clones. So we return for a tuple of t and u, we return t and u. And then this function, just for each of the return types, it adds a nested goal that type also implements either copy or clone. And then we use evaluate added goals and make canonical response again to get our final canonical response. Then we have alias bound candidates, which are the item bounds on associated types and opaque types. So if we have some rigid alias, like if you have t-trait, ts trait assoc is rigid, and if I would like to have an example. I guess that one is all right. So here we have t-trait and t-assoc. So if we now use x.into, we look at the item bounds of the associated type. There's an into u32 item bound, so that works. Cool. Then object-bound candidates is if you have didn't trade, that one implements trade, or if you have didn't trade plus send, that it implements send. Then blanket impulse, which are just ordinary impulse, except that they're for some type parameter as a self-type. And parent env candidates are the where bounds of the current function. And then this also exists in the alt solver, though the alt solver is a bit more aggressive about it, which doesn't impact behavior as far as I know. But yeah, if we are in the coherence or integrate mode, then we check whether the current trade ref is fully knowable, which is pretty much during coherence. We have to make sure that we don't consider goes to not hold, which may actually hold, and that may actually hold could also be that either a like sibling or downstream crate adds an impl, or like the upstream crate adds an impl which it is allowed to do in a backwards compatible way. So you have to make sure that if they're not if these impulses get added, that this doesn't cause coherence to suddenly fail, or coherence isn't even possible to know about downstream crates. So what we do is, if a crate would either be backwards compatible in an upstream crate, or would pass the orphan check in a downstream crate, if that is the case, we add an additional ambiguous candidate to represent, hey, there could be another impl here. So that's what we do here, and that's also what we do in the alt solver, where in the alt solver we completely skip candidate assembly and just return ambiguity. But this end result is the same. So that's how we assemble candidates. Are there any questions about candidate assembly? Apparently not. So once we've assembled all the candidates, there could be more than one, and we have to eagerly merge them into a single candidate. And that happens in merge candidates, which is like very simple for now. If there are no candidates, we fail. If all candidates have the same result, we succeed. Or if there's a candidate which has no inference constraint, we also succeed. So if something's like trivially true, we also succeed. I'm not totally sure that we're going to keep that one, but it doesn't matter for coherence, so that's good. And if there are multiple candidates and they don't have the same response, we fail with ambiguity, and that's what happens in Flounder, which just fails with no constraints, and either ambiguity or overflow, depending on whether any of the candidates resulted in overflow. Because if like one candidate fails with overflow and one would hold, then if the candidate with overflow would actually end up not holding, if we were to like recurse deeper, the result would change. So if there's any kind of overflow and we have ambiguity because of that, we also return overflow. That is the basic structure of the solver. And another very big change, I guess, from the old solver is the way we handle normalization. The core idea is that the new solver does not rely on things being normalized anywhere. So you can pass some unnormalized goal into the new solver and it can handle it completely fine. And the way we do that is by using the function structurally normalized tie whenever we would like match on the tie kind. So whenever we actually make a decision based on what the type is, we then lazily normalize at that point. And that is used a bunch of times. For example, at the start of assembly, right at the start of like for trade goals, and also for like when normalizing associated types, we immediately try to normalize the self type as much as possible. And there are some goals where we have to also structurally normalize other types. And structurally normalize only normalizes the like outermost type constructor. So if you have a vec, a vector of an associated type, structurally normalized does not normalize the inner associated type because we only match on the vector itself. And then if we were to recur into the fields of the vector, or more likely like for built-in traits, if the trait is implemented for like a tuple, structurally normalize first checks if the tuple is not an associated type, and then we have the nested goals where we look at the inner types, and then we structurally normalize those. But we don't eagerly like recurse into the type when structurally normalizing. And yeah, that's pretty much how normalization is handled in the solver. Whenever we would like match on a type, we first just call structurally normalize. At that point, we know that it's either a rigid alias, so an associated type where the trait bound only holds because of like the where bound, or just some rigid type. And if it's not, it's an inference variable. So that means that matching on the type is a lot nicer. Questions? Anything I should talk about right now? Input. What's your favorite pizza?
Pineapple.
Wonderful.
So I do have a question, if I
Yes.
can ask. So you were talking about these built-in impls, and I see that in the candidate source, most of them you don't distinguish between them. So it just says like candidate source, miscellaneous built-in impl. Would there be any interest in being able to differentiate between the different impls that are used?
So that's an interesting question. So for each candidate, we have the candidate source. So when assembling candidates for trade goals, we have different candidate sources. And like for impls, we have a unique candidate source, which is just the def ID of the impl. Mm-hmm. For like where bounds, we also have their unique index in the environment. Mm-hmm. But for alias bounds, like we don't know which alias bound it is. We don't have an index there. And for built-in impls, if we look at the source, like we have it for some of them, but not for all. And
so I guess my question here would be like the MISC at the top.
Yeah, exactly.
Could we, expand that out into some sort of, these things are all equal, but here's an index into what they are, or like some way to recover which one was used?
So originally, we didn't want to have these impl sources at all, because our goal was that like in the old solver, depending on the exact impl source, we do a lot of like weird special casing. Like if we have a built-in impl of that kind and a built-in impl of that kind, which one we drop is kind of arbitrary. But so originally my intention was to like just not have that information at all, so that we can't make decisions on it, because if you don't have the information available, how could you change behavior based on it? And that sadly didn't work out, because some of these actually need special behavior. So that's the reason why we added them. Tuple unsizing and trade upcasting are both still unstable. So we need to like, when that's what happened in select, when we encounter them during coercion, we emit a unstable feature error. And also trade upcasting and object are used when figuring out which imp to use, like the right index in the V table. So that's needed. For other impl candidates, I'm not strictly, so I'm not opposed to adding more information. It would be very much doable. Like it's not necessary for the solver, and we originally didn't add it because we wanted to actually avoid having that information available. But given that we now already like have like this information in some cases, I don't think there's any harm in having it for all of them. So
I see.
Yeah, I think it's fine to add more. We just didn't.
I personally would be interested in having more richer information for a candidate source, but I'm also happy to
yes.
I'm also happy to like add a patch to the compiler or something to add that, so you don't have to do it. So that's fine. Okay.
So it shouldn't hurt performance. It shouldn't do much. Yeah.
Okay.
So I think we would accept it.
Okay. Thanks.
Right. I also have a question. I don't know if it's like interesting to talk about, but what about the distinction between alias relate and normalizes too? Like why? Like what's the motivation for normalizes too?
That is very interesting to talk about.
Yeah, because it's like still undecided, or?
Because it's the most complex part of the solver.
Right. Okay. Cool.
So we have, if we look at all the possible goals you have to prove, there are a lot of them. And there are multiple which are related to normalization. There's normalizes to, there's alias relate, and then there's also clause kind projection. And these are all different in very subtle ways, which is wonderful. The easiest one to get out of the way first is projection. So projection is the thing which can actually be in where bounds. If you have team from straight, a silk equals U32, that's a projection bound. And we use them when normalizing in the new solver, but actually prove them in a very different way. We prove a projection goal by simply emitting alias relate. So projection goals get immediately mapped to alias relate. So the only two goals we actually prove in the new solver are alias relate goals and normalizes to goals. Alias relate is used to one, deeply normalized, like, well, not deeply, to structurally normalized types. So if we can look at the impl of alias relate. Alias relate is trinormalized term, which just there it is, recursively uses normalizes to. So that's the big difference, where normalizes to is like one-step normalization. So if you have an associated type, you figure out its impl and then instantiate the value for the associated type, which could be yet another associated type, which you then have to normalize again. So that's the point of normalizes to, that it like normalizes by one step. And alias relate is actually used to like normalize until something is rigid. And alias relate is also like a bit more general, where if you have a like an associated type on one side of the alias relate goal and an inference variable or some like rigid type on the other one, then it's just fully normalize the alias and then equate. But alias relate also handles like equating two aliases, which happens by fully normalizing both sides and then like equating the resulting rigid types. So since like normalize 2 is just this one-step normalization, which is also only used in alias relate. So normalize 2 is like a core building block which is used by alias relate to like do this full normalization and to equate associated types.
Perfect. Thanks. Makes a lot of sense. Yeah. Great.
Does this mean in theory you could get rid of the projection clause kind?
Yes, so projections do exist as where clauses.
Mm-hmm.
So we have to be able to represent them as clause kind.
Okay.
But like ideally, if we didn't have to care about performance and whatnot, what we could do is have the predicate kind used like for goals, like if we have to prove stuff, for that to be completely separate from clauses. So that like projection would be a clause, but not a predicate.
I see.
Yeah, so that would work because projection goals simply are just alias related goals with one step of interaction, which is kind of useless.
Okay, thanks.
If you still accept questions, I still have one more question.
I still have 45 minutes if you want.
Okay, great. Right, so like I know that you talked about, like, not in this talk, but you told me that during selection the new solver like eagerly looks at like selection of candidates, right? Like we eagerly look at where clauses if they hold, like in the new solver, but we don't in the old. And my question is like, doesn't this like affect semantics?
Yes, it does. Luckily, yes, it does affect semantics. It's limited because if there is like ambiguity, so looking at the old solver, we have like assemble candidates. That's not what I want. How is it called again? Okay, here. So in the old solver, we assemble candidates. And then if there is just a single candidate, we're assembling candidates, does not prove like nested where bounds or anything. And if assembly results in a single candidate, we immediately return that one without ever proving its nested bounds. But if there are multiple, we do actually like also evaluate all of them to like figure out whether after checking where bounds does only one candidate hold or not. So because that the solvers are a lot closer than you would expect, but there are some annoying issues. Am I sharing my screen or am I sharing VS Code?
VS Code.
Okay. So
no, wait. Like how would I be able to tell? Well,
do you see this? Oh, that's wrong. It's really painful that my screen.
Like I still see VS Code. Like I don't see any
okay.
other menu
So
bars. Okay.
then I'm gonna stop sharing VS Code and start sharing something else. Share window. I hope it's screen 2. No, it's screen 1. Hello. So there are some annoying differences. Like, is that already closed? Yeah, for example, that one. So you would expect that the old solver handles like always results in a fatal error if you have overflow. So you would expect that like we're free to do whatever we want when hitting fatal overflow, because that's something that can happen in the old solver. But because we do not check nested goals if there's just a single candidate, and we also do that during normalization, if there's a single candidate we use to normalize, we eagerly normalize using that candidate and only prove the wherebound of the impl used for normalization later. So even if the wherebound were to overflow, if we error because of the normalization before that, we never try to check the wherebounds. So that's like one example where this actually causes a difference in behavior and we have to handle it. There are a few more than that. I have to, can I remember any of those right now? I think you might. We do have one more issue. It's one of the first ones. All right. I guess that's kind of an issue of the same kind, where again it affects normalization, where you normalize and then lazily prove nested bounds, but when lazily proving them, you don't consider the like projection goal for the like as part of the cycle if you get a cycle that way. So stuff is conductive, which should not be. But yeah, it mostly doesn't cause many issues.
Okay, I see. Okay.
I actually don't have a good answer for why it doesn't cause more issues. Like, so yeah, I guess it doesn't cause issues because if there's only a single candidate, we'll like still prove the wherebounds of fulfillment. So it's not like we completely ignore them. We're just like slightly like a mix of the order or something. But we still, if there's a candidate, we still prove all the wherebounds later. So that's not a problem. And if there are multiple candidates, we try to evaluate all the nested ones before doing any filtering. So that way we also avoid like too big of a change in behavior.
I see. Okay, makes sense. I just didn't know that the old solver was like validating the where clauses like, during selection. I wasn't aware of that. Okay. Makes sense. Thanks.
All right. Gibt es other questions? Okay.
My main worry is still that I'm making assumptions about a new solver that I don't even know to ask the right questions.
Yeah, like, so yeah, that feels hard.
So that's why I think these sessions are good, because like you're going over a lot of stuff, and when I know there's something that I don't immediately understand, then I better ask.
So I'm thinking how to like maybe make it more useful, because like, what I did consider at some point was that maybe, like, I don't know, that would probably make the most sense as a recording, just like going through and adding a built-in trait and all the necessary steps, what actually needs to change for that.
Yeah.
And apart from that,
actually, we can do that in a very cool way by picking someone who doesn't know it yet and letting them do it with help.
Sure, if they are fine being recorded while doing it, then that would be great. Because of course I'm gonna already like know the answer. So even if I pretend like I have to look stuff up, it's all fake. So yeah, so that's something which would be useful. I think there's some areas where I know that they're complicated, but I don't know the best talk about them. Like the exact way normalization works is interesting, so it might be worth talking about. I could literally go through all of these issues and figure out which of them I used to talk about.
Maybe one question I have related to normalization. So in my mind, maybe this is just my bad, like incorrect assumption, but in my mind, I'm thinking of normalization similar to like unification in a prologue system. Does it work similar to that, or is it vastly different?
That's a very good question. The biggest issue is that I don't really know how unification in a product system works.
Okay.
With regards to normalization.
Okay.
So yeah, can you explain how that works, or would that be difficult?
I would worry it would just muddle the recording, maybe. If we're coming at it from different sides, it might not be so useful. I'll just have to keep learning a little bit more.
So it's, yeah, I don't know.
Probably the biggest thing about normalization and aliases compared to like the unification scheme that you might find in Prolog is aliases are typically like one way, right? I mean, even lazily, once you normalize, you don't keep the information that where it came from around. And that's probably different than how most Prolog solvers would handle unification.
I see. So it's really just about the directionality, than say anything else. Gotcha.
All right. Thinking whether there's anything else we should talk about today.
I mean, like, I don't know if, like, is this like the introductory, I don't know, talk about the new solver?
I don't know. It's just I want to talk, like, if there are questions, ask them. It doesn't matter how in depth they are.
No, like, I mean, in general, like, the new solver like solves like a lot of issues like related to like overflow, right? Because like, I don't know, is it like I know a lot of issues get solved by the new solver because like we don't overflow anymore on the projection goals, etc., etc. And that's like probably because like we like just normalize less, I suppose, like because we just structurally normalize or something.
So, okay, I think that's not quite right.
Okay.
So the new solver, like, it ends up actually normalizing even more than the old one. Like, it normalizes in fewer places, and it's not forced to normalize. But at least the way we currently handle the mere building is that we eagerly normalize at the end of here type check, so that in the mere you already know that because there are no more inference variables in mere type check. And if things might not be normalized, then whenever you would match on the tie kind, you would have to first structurally normalize again. And changing mere type check to do that, because it's not necessary with the old solver, is horrible.
Yeah,
so with the new solver, we also deeply normalize, but we do it at the end of your type check where there are no inference variables around anymore, which makes it a bit easier. And also, the old solver had some, for example, this issue 73 in the trade solver, trade system refactor initiative repo, where actually we get more overflow, both when normalizing and when proving trade goals, because we removed some hack in the old solver. So there's oops, I don't want the function, I just want the call. There's a check in the old solver where if something looks like it would result in overflow and infinite recursion, we immediately fail with overflow. But in the new solver, we don't have that check. So we actually end up running into the actual overflow where the old solver would eagerly fail with ambiguity. But the new solver is so better at handling overflow because we just don't fatally error.
Right, okay.
So that's what allows us to be that improves our handling of overflow, just not ending the compilation once we hit it once. And the main difference, at least the main selling point of the new solver, apart from just merging assembly and confirmation, because we now canonicalize each candidate, is that we handle aliases. Instead of the solver, we don't rely on associated types being normalized. And that's, I think, the biggest difference between the two solvers.
Okay, yeah, okay. Thanks for correcting my understanding there.
Sure. All righty. I guess, do we want to end it for today then? No questions? I'm going to end it for today. Have a nice evening or day or whatever. And bye.
Thanks for hosting this. Bye.
Thank you.
Thanks a lot.